In this presentation, we will compare and contrast two dose-response principles and how they relate to X-ray exposure. Anyone using X-ray as a diagnostic or treatment tool should be aware of these principles that undergird the necessity of radiation protection for you and your patients. Before we begin, I need to define a couple of terms: stochastic and non-stochastic effects. In the past, the terms non-threshold and threshold were used to describe these dose-response relationships. I'll pause for a moment to give you time to read the NRC, Nuclear Regulatory Commission's definition of the term stochastic effect. Now let's take some time to review some key phrases in the definition. Stochastic effects do not have a threshold of occurrence. This means there is no minimum dose that is considered safe. All radiation exposures carry some level of increased risk. As the dose increases, the risk of radiation exposure causing a stochastic effect increases as well. Stochastic effects do not increase in severity as dose increases. You can't get a mild case of cancer. Cancer either develops or does not, and the same is true for genetic damage that occurs with radiation exposure. The one redeeming factor of carcinogenesis or genetic damage is that they have a very low probability of occurrence, and the risk is outweighed for the benefits of an X-ray exam or radiation treatment. Here is the definition the NRC applies to non-stochastic effects. Do you notice the two major differences that occur between stochastic and non-stochastic effects? The first difference is easy to see. Non-stochastic effects have a threshold of response. There is a level that, if not exceeded, the effect will not be seen. Skin erythema, like a sunburn, should not occur for doses under 2 sieverts for most people, according to the International Atomic Energy Commission. The second, less obvious difference is that non-stochastic effects increase in severity once the threshold dose is exceeded. For example, a radiation burn, skin erythema, arising from a 10 sievert exposure will be more severe and will manifest sooner than a burn caused by a 5 sievert exposure. Let's take a look at how stochastic effects look from a graphical viewpoint. For this graph, the x-axis represents an increase in dose from 0 to some maximum value. The y-axis depicts the likelihood that a particular effect will occur. It is a percentage of risk increase and also begins at 0. The curve starts at 0 on both x and y axis and steadily increases from that point. There is no dose where an increased risk is not possible. Let's suppose the chance of cancer development for a particular dose increases by a risk of 0.6%. It is important to remember that an individual's risk is very small. For 10,000 exams, a 0.6% increase will amount to an additional 60 radiogenic cancers and 10,000 patients, and of 10,000 patients exposed, 9,940 will not develop cancer. On the other hand, from a public health perspective, the World Health Organization estimates that there are 3.6 billion X-ray exams performed per year. And if we apply the 0.6% increased risk to that population, it represents 21,600,000 radiogenic cancers per year. While the actual number of radiogenic cancers is not accurately calculated, by multiplying 3.6 billion exams per year by 0.6%, Even a fraction of the 21,600,000 underlines the importance of keeping dose as low as possible. Even though an individual's risk is low, from a public health perspective, it is not insignificant. There is no dose level where stochastic risk is zero, considering the number of X-ray exams performed yearly. It is important to keep radiation exposure low. Bottom line, as radiation dose increases, the stochastic effect also increases, and there is no safe level. Now let's take a look at non-stochastic radiation effects. For this graph, the x-axis will again represent increasing dose. A difference is that the y-axis now represents the severity of the effect. When we draw the curve, one thing pops out immediately. The curve does not intersect the y-axis at 0. If the exposure stays under the threshold dose, the effect will not happen. There is a dose where there is no effect, and this zone is considered to be safe. Once one exceeds the threshold dose, the severity of the effect increases. A light radiation burn becomes a more severe radiation burn. Additionally, the time between exposure and a manifestation of the effect increases. A simple test. Does this curve indicate a stochastic or a non-stochastic effect? If you said stochastic effect, you are correct. This curve has no threshold or response. What type of effect does this curve represent? And the correct answer is a non-stochastic effect. This curve has a definite threshold. Let's summarize some of the characteristics of non-stochastic effects. Non-stochastic effects have a definite threshold, that if not exceeded, the effect will not occur. Most radiographic, fluoroscopic, CT, and therapy treatments fall into the category of not exceeding levels where non-stochastic effects become visible. Non-stochastic effects tend to be acute or short-term. The exposure happens, the effect becomes apparent, healing or recovery occurs. This is not always true. Many early martyrs suffered from skin lesions that did not heal due to radiation decreasing blood platelet levels. Additionally, cataract formation does not heal due to the avascular nature of the lens of the eye. A common effect of overexposure is skin erythema, red skin. The exposure and the effect mostly happen within hours or days of one another. This makes it easier to realize that the exposure and effect are connected. When early radiographers realized that radiation exposure was harmful, they based early standards of exposure upon non-stochastic effects. In the 1930s, a tolerance dose was established by the U.S. and international radiation safety committees, which was based upon the skin erythema dose. This dose was equal to 0.1 to 0.2 Roentgens per day, approximately 1 to 2 millisieverts per day. Now a summary of stochastic effects. The most obvious characteristic of stochastic effects is the fact that they have no threshold of exposure. All exposures carry some level of risk. Stochastic effects tend to be chronic conditions. They manifest themselves over long periods of time. Stochastic effects tend to have a latent period between the time of exposure and when the effect becomes noticeable. This latent period can be in the order of weeks or even years. In the case of genetic effects, the person being exposed is not the person being affected, and the damage may not show up in a population for multiple generations. The existence of the latent period makes identifying cause and effect relationships difficult to say the least. The only way to observe some long-term effects is by statistical analysis of large exposed populations. It is based on the fact that a stochastic effect has no threshold, combined with the fact that X-rays are used to diagnose and treat billions of people per year, that make it necessary for radiographers to practice using the principles of ALARA, keeping a dose as low as reasonably achievable as a guiding principle in our profession. Thank you for your time and attention.